my plan is to record this class session. I have a student in COVID quarantine, so I'll record every remaining class this week. My plan is to choose different examples in the afternoon class than I choose in the morning class. And assuming this gets recorded okay, shouldn't be a problem, then I'll post the examples from the afternoon. So if you just like to see more varied problems, then you can go and check out those videos that I'll post. All right. So polar coordinates, I'm on the screen here. I can go to about there. Because of the tether, I'm going to have to use this portion of the board. So if you guys want to slide over somewhere, I think there's space. Socially distance and still see what we need to see. All right, so we want to think of polar functions, r equals f of theta. And you know, for y, a function of x, we imagine the curve moving from left to right. For x equals functions of y, we imagine the curve moving from bottom to top. Well, for a polar function, we will never ever think of theta as a function of r. We'll always, a polar function for us is where r is described as a function of theta. And as theta, the angle swings around, you know, the origin. For every theta value, there is a functional value. So the way we picture a polar curve is to imagine this curve sort of working its way around the pole. And for every theta, well, here's this guy right here is f of theta. That's the distance it is. So f of theta. And if I take the angle alpha, and over here at this point is f of alpha units away from the origin. So we picture functions moving around the pole, not left to right, not top to bottom. Okay, and you can create some very interesting things. For example, let's take a simple function, r equals theta. So the distance r from the origin is equal to the angle theta. When we start at 0, well, the angle theta is 0, so we're looking at the x-axis. R is 0 at this point. By the time we get to pi over 2 is about 1.57, so the point is 1.57-ish units away from the origin. And it just slowly increases. And then we keep increasing. And you know, then we can keep going around and around. So we get the spiral coming out of the origin. The origin in polar coordinates is called the pole. And so we, you know, create a situation where maybe it looks like this is not really a function, because for this angle, you know, I could possibly have this value or that one. But those are associated with different alphas. This one is with the first quadrant angle, whereas this one is like a fifth quadrant. We've wrapped around once and we're starting around again. So some interesting things can happen with polar coordinates functions. So what I want to do today is I want to have us kind of walk through sketching a couple of polar curves. And then, of course, the focus today is calculus. So I'll introduce some topics. They're only going to talk about two things: slope of the tangent line and area under a polar curve. So we'll sketch the curve, and then we'll talk about the related calculus, and then we'll do the calculations, and that will keep us busy. But first, I said way back when we started this chapter, the goal was to find different ways to describe curves in the plane, and so that we have a tool so that we can pick the easy way to do it. If you just think about circles centered at the origin, with radius A, let's just compare. So in rectangular, using rectangular functions, I have two fairly complicated functions. Square root of a squared minus x squared, and the negative square root. Right? We need one function for the top and another one for the, or I could use functions of y, one for the left, one for the right. The algebra would be similar. We discovered in parametry, excuse me, that we got, still took two functions, but we got simpler functions, just sine and cosine. Right? Easier functions to work with. So that's an improvement. But if we go to polar, we get the simplest possible function. That is a circle centered at the origin, radius a. Well, every point on that circle, how far away from the origin is it? A units. So we get a constant function, miraculously. So if we deal with circles centered at the origin, or, you're in physics and you have an object that's circular in shape and you want to introduce it to a coordinate plane so you can, use algebra, calculus, and so forth. If you can center it at the origin, then, you really, really want to use polar coordinates because there's the function. It's a constant function, as easy as it could be, right? If you watch the video from my colleague, as soon as he used the symbol R, he called it the radius, but he didn't ever connect it to a circle. Later, he set R equal to a constant and talked about a circle. But that's why we use the coordinate R, I think, is because the simplest possible function, a constant function, gives us a circle. And therefore, the R value, A in this case, is the radius. And so we use the symbol R as the polar coordinate for distance. All right, so in terms of functions, this is awful, this is okay, this is wonderful. And so, when we're confronted with this kind of a curve, then, our very first go-to technique is going to be polar coordinates. If we can do it, and there are other issues depending on the problem we're trying to solve. And some things like parabolas are never, ever very nice in polar coordinates. Lines actually are really nasty unless they pass through the origin, and then they're nice and simple. You saw in the video, it's just theta equals a constant if the line passes through the origin. Otherwise, lines are not very nice. All right. So that's the idea. And now let's look at an example. And like I said, I think we'll have time to do two examples, I hope, because we're going to work out the calculus as soon as we get the first graph on the board. And then my plan is to do two different examples in the afternoon. So here we go. Graph. R equals 1 minus cosine theta. We'll go, we have a cosine, the period is not modified. So like if we can do one revolution, then we'll cover every possible feature of the graph. Okay. Now, last week we set our calculators to parametry and we could sketch graphs, and it was fairly amazing the things we saw. We could set our calculators to polar, and then, when you go into y equals, you'll be presented with polar options. The function will probably be called R1, not sure. And then your variable would be theta, I believe. So we can graph it on our calculator, but what I want to do is talk through it so we understand the process. So we look at the graph on our calculator and we can make sense of what it says. So what I like to do is handle these by quadrants. It's not a circle, by the way. We haven't seen that before, I don't think. Well, there might be something like it in one of Nick's videos, I'm not sure. So we're going to do quadrant, and then we're going to analyze the cosine, the function that's present in our function. Actually, I need a column. Let's put a column for just theta. And then we'll have one for cosine theta. And then we'll have one for r, the functional values. So the first quadrant, theta goes from 0 to pi over 2. I think the later examples, my colleague Nick did a very similar thing. The cosine of 0 was 1, and at pi over 2, it's 0. So I analyzed by quadrants because the cosine has a real simple, predictable behavior. In this case, it goes from 1 to 0. And therefore, r, cosine starts at 1, so r goes from 0 to where? 1. Plug in your 1 here, get 0, plug in the 0 here, we get 1. Yeah, I don't know how this is going to work. Not sure I can get my polar graph on the, should be able to share my desktop. Please wait, system warming up. Go. There we went. Here we are. Cursor. Somewhere here. What in the world? There it is. Now, if I my zoom on here, find out. Okay, I think I need to come over and grab it. And then if I share the desktop, maybe that'll work. If I can find my cursor. There it is. Does that say share screen? Which one do I pick? That one. Cross my fingers. Is it working? Does anyone know? It says I'm screen sharing, so I'm going to assume we're good. All right. So here's a polar graphic. You've probably seen it before, just to help us draw a good graph. Notice that we have circles, concentric circles. There are 5 of them. I can look at this function and see that it's going to range between 0 and 2, right? If cosine gets out to -1, and it does, then the function is going to be 2. So I'm going to pick, like, I want to draw as big a graph as I can, so I'm going to pick this guy right here as my 1 unit, and therefore 2 is out here. And that'll go all the way around, and in between we have half radius. So we're going to start at 0 right here. I was going to do these color-coded. So we'll start with red. Start at the origin, and at pi over 2, we're up to 2. We end up there. Okay, and there's, you know, if with the sine or a cosine involved, there is one easy angle to fix, to calculate, to help us draw a more accurate curve. For a cosine, it's pi over 3. the cosine of pi over 3 is, I said it's easy. Somebody prove me right.
It's 1 over the square root of b.
Grant, 1/2. Yeah, I know because Grant was in my office and he supplied the answer yesterday. It's 1/2. And so at pi over 3, r is equal to 1/2, 1 minus 1/2. Okay, just to give me a nice reference point. So I went back to my red pen.
Thinking about your graph, so the cosine of pi over 2 is 0, right?
Yeah,
But so that should mean that 1 minus the cosine of pi over 2 is 1. Why did you put it at
oh, yeah, good question. Some of you else were wondering that. We end up at 1. Thank you so much for asking the question. At pi over 3, here it is. We're at halfway. So pi over 3, the halfway point is right there. Right? This guy is 1. Just a minute. Yeah, this point's confusing me. We're going from 0 to 1, and at pi over 3, we're equal to 1/2. Right there. How about that? And now we'll draw the graph. So as we draw it, r is gradually getting further from the origin while we're sweeping out this angle theta. And we need to go through that point. So we get something like that. Okay, quadrant 2. Theta goes from pi over 2 to pi. Cosine goes from 0 to -1, right? And therefore, our function, we left it at 1. We'll do this one in green. And when cosine gets down to -1, theta is equal to 2. Right? 1 minus -1. So we're going to start at this point. At pi over 2, we need to be out to 2, which is right there. And again, there's an easy point to calculate. The cosine of 2 pi over 3 is -1/2. So the cosine of 2 pi over 3 is -1/2, and therefore r is equal to 3/2. 1 minus -1/2. And that point is 2 pi over 3 is right here, and we're halfway out. We've made it to that guy. So we just keep gradually getting further from the origin. Yeah, we can't get outside this circle as we come in, but we're going to get super close to it, as close as we can get. So something like that. Okay, that makes sense to you? Quadrant 3. If our function is not too complicated, and I would put this one in that category, eventually you kind of see what's going on and you could maybe not provide all the details. So cosine now goes from -1 back to 0, which means, let's do this one in blue. We left the function at 2, we'll pick up there, and then we're going to go back to 1. And again, there's an easy point to find in there. It's what? 5 pi over 3. Pi over 3 into the quadrant 3. The cosine is negative, so we're actually just going to make the strip going back. So down here we end up at 1. We end up there. We go through a point corresponding to that one, which is on this line right there. And so something like that. It's actually, it should be over here. I can't quite read my labels. Right there. And we are headed into 1. And then quadrant 4, I think it's fairly obvious. Going to have a point right there. I'm just going to come back and so get a shape sort of like that. Analyzing it quadrant by quadrant. What would be a good name for that shape?
Looks like an apple.
Yeah. I think the official name is a cardioid, maybe heart shape. You could use it to give your special someone a Valentine. That'll argue it. All right. So we'll do another one, and then, like I said, we'll do some in the afternoon, different functions. So now I want to quit sharing, and we'll talk about some calculus aspects. See if I can leave the. It's not on. All right. Like I said before, there are two calculus topics I want to talk about. And maybe we're going to reference the curve. On Zoom, you can't see it right now, but I'll try to remember to show you a picture of it. Those of you listening on the video when we get done. So the first thing I want to talk about is slope of the tangent. Like what calculus seems to be rate of change. That's what we're talking about here. And of course, slope of the tangent is dy dx. Tangent line, the slope, it doesn't have anything to do with polar coordinates. It's change in y over change in x. So somehow we have to take our polar function and get the information out of it that tells me the rate of change of y with respect to x. Okay, there's a fairly easy way to do this using what we learned on Monday. That is, on Monday we learned that if we had a curve given parametrically, then we can find the slope of the tangent line, right? It's dy dt over dx dt. So it's easy to take a polar function. I'll show you how to do it. Not that one. R equals f of theta. And I can write it. Remember in the video, Nick derived a relationship. It's simple right angle trigonometry. You could have done it yourself. There's a relationship between rectangular and polar coordinates. Super important relationship to know. You know, when you come for the final exam, either have these guys memorized or write them on your note card, which you will have available. There's one other one which I don't think I'm going to use on this one, but I'll just list them all together. We could even write one for theta, but not sure we're going to need it. So relationships, like if I want to go from polar to rectangular or rectangular to polar, those three equations generally can guide me forward. All right, so it's easy to take our polar curve and write it in parametric form. It is all I have to do is slide my R value in right here and here, just substitute. So the polar curve in parametric form. And we do it because we already know how to find derivatives. Parametric form, x equals f of theta cosine theta, y equals f of theta sine theta. Because of our relationship, we know, I mean, we're lucky that we know exactly the formula for x and y, which is what we need to have parametric form. So now we'll just use what we learned on Monday. But our parameter obviously is theta, not t. So we're going to take dy d theta and divide by dx d theta. Both x and y are products, functions of theta. So we're going to use the product rule for y. Take the derivative of the first function times the second plus the first function times the derivative of the second cosine theta. And I'll do the same thing down below. Cos theta. And then I'm going to get minus. The derivative of cosine is minus sine theta. All right, so there it is. Nice little formula. We can ignore this intermediate step. That's how we find the slope of the tangent. Right? We can write it in a slightly more compact form. I'll write it up here. By just using r instead of recognizing that r is a function, so I can put a prime on it, that means derivative, plus r cosine theta. And then we have r prime cosine theta minus r sine theta. So whichever way speaks to your heart, they say the same thing. Okay. So we can use what we learned on Monday. It gets us a fairly nasty expression. We might have hoped for better, but you know, at least we've got one. There's like a 98% chance you'll be asked to demonstrate knowledge of this on next week's final exam. So, you know, memorize it or plan to write it on your note card, one way or the other. And let's follow up with an example. Find the slope of the tangent. To r equals, that function was 1 minus cosine theta, right? I want to use the graph on the board. At theta equals r/4. So I lost my polar graph paper, but I think the picture looks something like that. And again, on the video, I'll remember to show you the picture. If it turns out it's right, my guess without the polar graph paper underneath it. And I'll show you the picture when we're done. All right, again, I picked a fairly nice angle here. You know, there's some work for us to do. But here we go. dy dx equals r prime. Well, r prime is sine theta, right? So we're going to plug pi/4 in there. And then we're going to multiply by sine theta. Another one. Then we're going to add r, which is 1 minus cosine pi/4 times cosine pi/4. We're going to divide by r prime, another sine. But now we'll multiply by cosine pi/4. And we'll subtract r sine pi/4. Nope. 1 minus cosine pi/4 times sine pi/4. What is sine of pi/4? Yeah, 1 over square root 2 or square root 2 over 2, however you like to write it. I'm going to pick the first version. I see a lot of squares going on, which I'm going to like. 1 minus square root of 2 times 1 over the square root of 2. Cosine and sine are equal. pi/4 is 45 degrees. Our legs have the same length. So, you know, I picked a nice point for us. And then down below, I get 1 over the square root of 2 times another. Cosine is the same. Then we're subtracting 1 minus 1 over the square root of 2 and multiplying by another 1 over the square root of 2. Now we just have some arithmetic to do. Plus 1 over the square root of 2 minus a half, I believe, is the numerator. Check and see if I'm right. And then a half minus 1 over the square root of 2, distribute. Minus minus plus half. I believe we get -1. That's our answer. Wrong.
I got 1 over the square root of 2. So the thing on the bottom, you have
Yeah, the halves don't cancel down below. I thought they were going to, but they don't. And just to make it pretty, I would like to multiply by square root 2 over 2. 1 over the square root of 2 minus 1. It's a positive number. You know, it's not a huge number. Square root 2 is 1.4, so consistent with the picture. And I promised tangent right there. So there's the tangent line. And see if I can get it in the picture here for those watching. It's not going to be very good. There's the cardioid. You can see it. And the black line is the tangent line, whose slope we just computed. Questions? All right. The second calculus topic. So we came up with this nice formula, you know, whichever way you like it for the first one. So, you know, we couldn't really finish our material without one more chance to talk about Riemann sums. So we'll take our chance here and do it. The second one is area under, and we'll figure out what it means under a polar function. A little different than for a rectangular function. Let me just show you a picture. So here's our curve. It's wrapping around the pole. That's how we think of it. We're going to start with some angle, call it alpha. And we're going to go over here to some other angle. We'll call it beta. I sure hope this is working. It doesn't say I'm sharing the desktop, so all right. And so the area under, I'll shade it in red. It's just all of this between the function and the pole. So all of it. So, you know, maybe there's a better word than under. I put it in quotes to suggest there might be, but I don't have one. All right. In Calc 1, we learned that to get area, you just need to integrate the function. But remember, that's with a rectangular function, we could approximate the area under curve with rectangles, whose height was the function, whose width was delta x. And so just the function, we needed the delta x for the Riemann sum, and just the function showed up. Here, we're not going to approximate that area with rectangles. So if we integrate the polar function, it's not going to get us area. I have no clue what it's going to get us. And we're never going to do it if we're doing things correctly. So what we have to do is find a way to approximate the area. And you know, I approximate it. I can't get it exactly. And I really, really hope I can approximate it in a way that has the form of a Riemann sum. Okay, we need a little reminder first. And that is, you know, we're not approximating with rectangles. Instead, I'm going to use the arc of a circle. So let's take a circle, radius A, I guess. I'm going to take a chunk out of it. A piece of pie out of it. And I know the angle. William.
is the area A theta?
What do you mean by A?
Oh, I thought that was an A, that it's an R. The radius, it looks like an A.
Yeah, so this is just some polar function. All right, so the area of that, this is called a sector of a circle. is 1/2 r squared theta. You remember from your pre-calculus classes. Or maybe you remember talking about it if you don't remember the details. That's kind of an ugly, let me rewrite it, 1/2 r squared theta. And it's crucial that theta be measured in radians. If you forget that formula, you could easily derive it. I think it's obvious if I double the angle, I double the area, right? And so you can set up a proportion. We know there's pi r squared in the whole circle, which corresponds to 2 pi. So anyway, here's our formula. So I'm going to take, because I don't know how to get it directly, I'm going to partition the region, by splitting the interval alpha to beta into equal pieces. And each one of these pieces will say has an angle delta theta. Let's pull one out here and work on it. So here's our sector. I mean, it does something like that. The angle is delta theta. It comes from our partition of the angle alpha to beta. And then what we're going to do is pick a particular angle inside here. I'm going to pick this one right here. We're going to call that angle theta. It's on the ith subinterval, so I need a subscript. And how do I denote the guy that I pick out to represent all of them in this angle? What do we call it? We have a special notation. We use an asterisk. Yeah, he's the star. I choose him to represent all of the angles in this angle, delta theta. And then what we're going to do with that guy is form a sector. It's going to be an approximation. So I want the sector of the circle whose radius is the function at theta I star. And I can't really draw this very well. So the blue line, partly I can't draw very well because that's finished. So this is along the circle. The blue is a circle. It's this piece right here. So I use theta I star to get me the radius. And then I use that for the whole thing. And it's going to be an approximation. So the area on the ith subinterval is approximately equal to the area of that arc of the circle. Now, the crucial thing is that if the angle gets smaller, does the error in our estimate go away? What do you think? Yes or no? Yeah, sure. The curve and the circle we're using to approximate, they're going to come closer together. So I get 1/2. My radius is the function at the chosen value, theta I star. And we have to square that, and my angle is delta theta. Angle on the ith subinterval. So the total area, I'll just sum over all of these guys. There are n of them. And what do you notice? It's a Riemann sum. It has a function of a point on each subinterval, and it's multiplied by delta theta. Okay, a Riemann sum, which means we did all the hard work. We just need to recognize. Therefore, we take the limit, it gets us exactly the area. Is the integral from alpha to beta, 1/2 f of theta squared d theta. So if you've forgotten all about Riemann sums, you can still use the formula. You have my permission. It's different. For rectangles, all we have to do is integrate the function. But because we're not using rectangles here, it's a little different. And maybe it's a little more complicated. Example. Find the area enclosed by r equals 1 minus cosine theta. Okay, we're actually not going to find the area, we're going to find the integral. And then in the interest of time, I wanted to do 2 examples. Maybe we'll talk about how we would evaluate it, but we're not going to crank through it. That's stuff we've all learned before, we're experts at. All right, I'm going to use symmetry here to solve this problem. Actually, we don't need to do it. The area is, so remember, this is the origin. And, you know, as theta goes from 0 to 2 pi, we just get the functional value. So this fits the assumptions, a polar curve moving around that we use to derive the formula. So all we have to do is use the formula. Notice I can bump that 1/2 through. To get all of the area, I need theta to go from where to where? 0 to 2 pi. I was going to use symmetry. I could go from 0 to pi and double it, but probably doesn't really save me any effort. The function is 1 minus cosine theta squared. The formula says square it d theta. There we go. That's the integral that gets me the area of that cardioid. So now let's take it one step further. 0 to 2 pi square 1 minus 2 cosine theta plus cosine squared theta. D theta. I'm changing my mind. I'm not going to do another example. We'll just finish this one off. Theta minus 2 sine theta, antiderivative. Anybody remember the antiderivative of cosine squared?
Is it theta over 2 plus sine 2 theta over 4?
Okay, well, yeah, I asked you to memorize it. Maybe you remember it like Will said. That I don't think that's the way I wrote it on the board. I didn't write it that way either. Sine 2 theta. 0 to 2 pi. Right, so this guy, remember I asked you to memorize. And therefore you did, so I'll write it in past tense. Memorize it so we can just like roll it right out. So theta is 2 pi. Sine of 2 pi is 0 plus 1/2. Plug our 2 pi in right there. The sine of 4 pi is 0. See if anything happens at the bottom side. 0, 0, 0, 0. Nothing happens. At 0. If I would have had 1 minus sine theta, then it would happen. I'd have a cosine sitting in there, which is not 0. So what? 2 pi plus 1 more pi makes 3 pi. 3 pi over 2. That's the volume. Sorry, the area of that particular cardioid. I hope that's the right answer. No one sees a mistake, right? Yeah. Any questions? All right. So I will do another example, a different one, quite a bit different one in the afternoon class. What I may have to do is do some more examples and post them on XYZ. I could either do them, like I've been doing lately with the photograph, or if I feel like I need to explain, I could maybe make a quick video, or maybe I can find good examples online and refer you to those. I'll start with the calculus professor. The next series of his videos is the calculus applications of polar coordinates. Are there any questions? All right, we'll see you Friday for a recap of the semester and prep for the exam.